going to turn things over to Steve Spector, who is our speaker tonight. Dr. Spector is from Draper Laboratory. He's a member of the technical staff there and a group leader as well. He's leading efforts in integrated photonics, imaging, and Lidar. He received a BSc in engineering physics from Lehigh University in 1991 and a PhD in physics from the State University of New York at Stony Brook in 1997. He previously worked at Lincoln Lab from 1999 to 2015, where he led silicon photonics efforts and was also responsible for a number of projects in nanofabrication. And before Lincoln Lab, he was a postdoctoral fellow at Bell Laboratories, where he developed EUV lithography. If I could just ask everyone to mute themselves, please. Thank you. So his talk tonight will be about chip-based beam steering with optical phase arrays and lens-assisted beam steering. So Steve, with that, I will turn things over to you.
All right, let me try to share screen here and keep going. Okay. And just give me a sec to orient myself and I'll start. Okay, great. So yes, my name is Steve Spector. I'm at Draper Laboratory. I'm going to talk, Hillary just said, chip-based. Yep. Everything good? Okay. Chip-based beam steering with optical phased arrays and lens-assisted beam steering. My email is here. I'll be later in the talk too if you don't get it at this point. So yeah, please feel free if you have any questions that we don't get answered to email me, and I'm happy to chat more about this. So start by what is solid state beam steering and why you should care. Well, beam steering is basically, so there's two pieces to that. The first is beam steering itself, which is putting optical power where you want it. And this is useful for things like Lidar, optical communication, imaging, remote sensing. I'm going to talk today about Lidar and imaging. In some sense, those are remote sensing, but you know, those are the two main topics I will talk about. And the solid state part is, you know, a convenient way of doing it. You want to move the beam without moving parts. And you want to do this because it can be low cost, compact, reliable. It can be very quickly because there's no big thing you're trying to move. And so it has lots of advantages over, say, you know, mechanical motion of moving a mirror. Some of the technologies I will talk about today are Mem switches. So you could arguably say they aren't truly solid state. You know, there is motion there, but the motion is only on the order of a micron or so. So they really, to the outside user, they really appear to be solid state. They have all those advantages.
Steve, before you move on, we're seeing the speaker view of your presentation, not the presentation view.
That's interesting because I don't even have the second monitor. All right, how do I do that? Does anyone know how to fix that?
If you go to full screen,
like this button here.
And then you change the display setting and swap display up there.
Well, I'm seeing the presentation fine.
Yeah, no.
Oh, there are two pages.
So, is that better now?
No.
So up there, there's a display.
Oh, now it's okay.
Oh, there it is.
That's
okay.
good.
Okay, great. Thank you for pointing it out. Okay, so yeah, so I'll outline my talk now. So I'll give a brief introduction to Lidar, then I'll talk about two solid state beam steering methods, optical phased arrays and lens-assisted beam steering, just like my talk. And for both subjects, I'll go a little bit into what other people are doing, and then I'll talk about what we're doing at Draper. And our Lidar technology will finish with this MEMS grading switch that we think is really unique and very useful. A shameless plug here. I just wrote a review article. It turns out that was on lens-assisted beam steering that was published last week. So, you know, please, you know, look at that if you're interested. And another note is you'll see the footnotes of a lot of the references. I will have a page at the end where I just put all the references. So if you want, you can kind of screenshot that and have it. Okay, so on to Lidar. So what is Lidar? It's, you know, stands for light detection and ranging. And in the simplest form, you send out light and you start a timer, wait for the light to return and stop the timer and see how long it took the light to go there and back. So that's a pretty simple way of doing LiDAR. And that's known as what's direct time of flight. That's one way to measure the time of the light going back and forth. Is direct time of flight measure. Direct time of flight, which is what I just described. You send out a pulse of light, start a timer, and when you get detection and return, you stop the timer and look how long it took. And this is has the advantage that it's pretty simple. It's fairly accurate. Has the disadvantage that you need fairly fast electronics, right? Because you want to time things very accurately to get good range resolution. Also, all your laser power is in that pulse, so you have high peak laser power. You're not spreading the power out over time. Indirect time of flight. Oh, and I should note that's used a lot right now in automotive. It's pretty much the standard automotive LiDAR method. It's also in some cell phones, such as the iPhone. I think the Pro series uses that method. Anyway, another method is indirect time of flight. This is sometimes called amplitude modulation. And what you do here is the light that you're sending out is being modulated at nominally a single frequency, although multiple are used. And then you modulate your detection at the same frequency. And so what you get is a beat, which is gives you the relative phase of the signal you sent out in the return. So that phase, that strength of that signal is the phase of those relative oscillations. And you can use the strength of that signal to get a range. So this is good because it's very easy to implement. You don't need very fast electronics. You can get by with a lower speed oscillator than say the very short pulse you need in a direct time of flight. It's more CW-like. You're spreading your power out. The problem is it's not as accurate as reliable. You can imagine you're trying to get this very analog signal of how strong that intensity is when you beat these two signals together. And it's hard to get a super accurate measurement, and it's easy that things can throw that off a bit. The last method is coherent. Sometimes you'll hear this called frequency modulated constant wave, or FMCW. And there are other ways of doing coherent, but FMCW is the most common. And here what you're doing, you're going to split the light coherently, mix the return signal with the split off signal. And the nice thing about this is, well, it's a coherent mixing. So you get optical gain. That is, the strength of your signal not just depends on the strength of the return, but also it depends on the strength of that signal you held behind, which is the local oscillator. So this is really useful because you're not limited by detection efficiency in your signal strength. It's also virtually immune to interference because the only signal that's going to really coherently interfere with that local oscillator is a nearly identical signal, the signal you sent out. So any other signal coming back from like another car, or I'm sorry, another LiDAR, or the sun, it's just going to give you kind of a smeared out background. It won't give you a true signal. You also get velocity information. So this is great. Why does everyone do it this way? It's harder. You need much more demanding laser and electronics requirements because it has to have that coherency. You have to, I'm not going to go into detail, but you do certain things to signals to get that range measurement. And you also have the spatial coherency requirement. Not only do you have to have a single frequency laser with good temporal coherence, you also need spatial coherence on the signal you're receiving to get good interference between those two signals. So that limits how much collection efficiency you can have. Okay, so I just described how to get the range, but you also want directional information too in a LiDAR system. And so that's where the beam steering part comes in. And so here's some methods that are used for beam steering today. And it's going from left to right. Sort of the most common or basic would be the mechanical method, where you just focus the light, bounce it off a mirror, and then move the mirror. And so you spin the mirror typically to rotate the beam around. You might tilt or tip it too. And this works very well. It's probably the best optical performance you're going to get, but it has its obvious disadvantages that it's a mechanical system. So you can't, it could be big or bulky, it can have reliability issues, it can just be expensive. So these work really well, but people are hoping for better in terms of the convenience of it. So mechanical systems can be miniaturized, and one way to do that is with a Mem system. And so now we've gone from a big mirror to a small mirror, and you can build this in a MEMS facility. So now it becomes cheap and small and all those nice other properties. The problem is it's a small mirror. And so with a small mirror, you can only move so much light. So that means you're not going to have a very well-defined beam, perhaps, and you can't collect a lot of light with this method either. So I'm going to skip to the other side and come back to the middle because that's where the talk is. But I also want to bring up the last two methods, which are wavelength steering. And here's where you basically send a light through something like a prism or a grating. It directs the light, depending on the wavelength, into a different direction. And so you can steer the beam just by changing the wavelength. I don't know of any systems that do this on its own, but it's very, very common, and we'll discuss this more, where you'll combine that with another method. So you'll use one dimension of steering by changing the wavelength, and you use one of these other methods, could be any of them actually, to steer in the other direction. And then there's a flash system, and flash is no steering. You just send out a big bright pulse of light in all direction, and you rely on your detector array for directional information. And that works pretty well, but you can only get so much range typically because you're sending out the light in all directions. So the intensity of light is going to drop off pretty fast. So let me turn to the two methods in the middle, because that's where my talk is going to be focused. Optical phased array works by coherently combining the light from a bunch of emitters, and get to how detailed that works in just a second. But the nice thing about that is there's no moving parts. And there actually is no lens either. Lens assisted beam steering, basically here all you're doing is switching the location of where the light's coming out of a chip, and then a lens does the beam formation for you. So that method does use a lens. Before I go on, I want to make an apology or an admission that these are pretty broad subjects. I'm going to talk a lot of different things. One thing I'm leaving out is the optical chips, a lot of the details of the chips themselves, such as waveguides and switches and things. There are some exceptions with that, but I do apologize. I think some of the audience is going to be familiar with how photonic integrated circuits work and how these different structures work on a chip, such as waveguides and resonators and Mach-Zehnder interferometers. If you don't, I'll go through it a little bit to just let you know what they are, so you can follow the talk and you can research them later. But there's only so much I can put into an hour. So anyway, so the optical phased array works by a principle where you have an array of emitters and they add coherently only in the desired direction. So what do you need? You need an array of emitters, and to get the coherence in the right direction, you need a way of adjusting the phase between those emitters. So as I said, there's no physical movement here. You just need to alter those phases to steer. This is actually something that's been done a lot in radar. It's pretty common because a large radar aperture is tough to impossible to mechanically steer. So this has been very useful in radar systems. But it's much easier to do in radar and optics because the size of everything scales with your wavelength, and optics has a much smaller wavelength. So in a radar, you can have a lot of processing behind each antenna. In optics, it's much harder. So let me describe how a phased array works. So if you start with a single emitter of light, single antenna, you get the spherical wave coming out of it, just like if you dropped a rock into a pool, right? So light's diverging in all directions. If I place an array of identical emitters, and they're less than one wavelength apart, and I'll talk about longer wavelength or greater spacings in a minute, but at less than one wavelength apart, everything's continuous. So you just get this continuous wave, this flat plane wave going across, and this is a beam going out from left to right. So if I want to tilt that to point it in a different direction, so right now the light's going straight from left to right and projecting a beam, I tilt the phase so that now the light's heading slightly downward in this downward angle. And so if you look closely at two if you look closely at two antennas, what you can see is that the phase of this one here, I hope you can see my mouse, is ahead of the phase here. And so basically, as you go, to get the steering, you can see that what's happening is that as I go up this array, each element has a phase ahead of the one below it. And so that's how I can steer the light, by adjusting those phases. Now, as I mentioned before, this works, that picture is sufficient if the elements are less than a wavelength apart, but if they're more than a wavelength apart, it gets a little more complicated. So let's consider the first case now, where we want to point the beam in this direction as shown. So we add a phase so that we had this blue path here. So I basically, at this point along the dotted line, they're in phase. So I have the phase of this element is trailing this element here by this blue path. And that means that they're now going to add into phase in this direction. Now, if I'm longer than a wavelength apart, I can add a wavelength to that path. So in addition to the blue, I now have this red path, which is one wavelength long. You go one wavelength and everything ends up in phase again. And so both these angles are in phase, and we'll add and get the beam going in both directions at once. And an example, here's an optical phased array. This is a two-dimensional array, so you get these dots in all directions. You get these grading orders in this 2D structure. So how do you deal with these grading orders? Well, one thing we've seen or people have done is they've made the array irregularly spaced. So this means that you don't get everything adding up in one direction as you add a wavelength. Instead, it adds up in random directions. So this keeps those higher orders from being in phase. Power still goes in unwanted directions, though it's just spread out. It also complicates the phase control a bit because you're not adding, every element is a different spacing, so every element has its own phase it needs to point in the right direction. You could use a lens array, and I'll talk more about this in a little bit. This works pretty well, but it's not a perfect solution. You still get some power, ends up in the high orders. And a steering range is still limited fundamentally by the element spacing. So I can't steer to wide angles doing this, but I can at least keep those higher orders. I can just steer within an order, but those higher orders don't happen. And of course, it requires an additional optic, which may be less than ideal. The final solution is the brute force approach. Simply make the array tightly spaced so they run less than a wavelength apart. This can be done, but it's tough because the close waveguides can couple. And there are some solutions to that, but it makes it tricky. And also, reasonable aperture sizes are going to yield a very large number of elements, as we'll see. So this is how a typical photonic integrated circuit would implement optical phased array. So the gray box here is what's on the chip. Typically, you're going to have the source off the chip. Within the chip, you're going to split the light into many different paths, many more than shown here. And each path is going to have its own phase adjustment control and a grading. And what the grading does is it emits light out of the plane of the chip. In addition, the direction of that emission is going to depend on the wavelength. And so how this works in a system is I actually have these two methods now to adjust the direction of the light. In one direction, going across the grading, the changing the wavelength changes the angle of emission from that grading, or from all the gradings actually. To steer in the other direction though, I'm using the adjustment between these phases that you can see go across this direction. So I hope that's clear, but basically it gives you 1D steering, change the wavelength to steer across the grading. The other direction, in and out of the board, you change by using the phase array, the relative phases of these elements going in and out. If that was a question, I couldn't understand it. I'm sorry. So an example of this is done by a company, Analog Photonics, started by a professor at MIT. They've recently published some work on this, where they've created an 8,000, more than 8,192 element array So this is how many elements it took. It takes a lot of elements. So this is an amazing feat they did, but it does, both show the capability and the challenge here. And by spacing elements of 1 micron, they get 100 degrees of steering, because the element spacing, remember, I didn't describe this in detail, but the element spacing determines how much your steering angle is. The tighter you get it, the more you can steer. Basically, you can steer until you have another wavelength of path in there. So get them close together, you get 100 degrees of steering in one direction. In the other direction, they use degrading, right, to steer by wavelength. They tune from 1515 to 1635, so pretty broad, and they get 17 degrees of steering. And to get this element, to control this element array, they need a digital analog converter for every single phase element, right? So they have 8,000 digital analog converters. They've got to get signal onto this chip. So they did it by creating 8 CMOS chips and flip chipping, bonding them to the optical phased array. So it's a very big chip. And the aperture is still fairly modest at 8 millimeters by 5 millimeters, although for an optical phased array, this is pretty record breaking. Okay, so I'm going to switch gears a little bit and talk about what we were doing at Draper, which is something different. We're not trying to steer a beam for a LiDAR or to point a beam in a particular direction. What we're really trying to do is image. And so unlike the LiDAR application, when you're imaging, you don't have control over the wavelength. In fact, you want to collect a lot of wavelengths at once. And so you have a very different requirement here. The main thing is, which leads to 2 things. One, you want a full 2D array because we want to be able to steer in 2 directions, and we can't use that wavelength trick anymore. So we have to do a full 2-dimensional phased array. Also, to get broadband operations, you have to make all the paths equal, because you don't want, if there's differences in paths, then you get a difference in phase with wavelength. So it's done using this sort of what we call an H tree, which is this fractal pattern. And so if you trace all the paths, you basically take a path from each one of these, they combine again, they combine again, they combine again. So you collect the light and combine it along this path. And each, other than the fact that some turns are left and some turns are right, all the paths are identical. And here's another picture of that. And you can see, here we show 2 different paths and how, all the way out to the end, they're basically the same, other than some turns being left or right. And it's true for every element on here. One thing you'll notice, though, is that there's a lot of waveguides between these elements. So you can't get the elements that close together. So in this case, they're going to be separated by 100 microns, which is much larger than the wavelength, which is like about 1.5 microns. So this is where we use a lens array. And what a lens array does, it removes the higher orders. So if you look at the picture without the lens array, you have this very divergent light coming from each one of these sources, which is a grating on the chip. I'm turning it around to emission just because it's easier to understand, but it works in both directions. And then if you put a lens array here, what happens is the lens essentially collimates the light. You put it at the focal plane of these emitters, and you get collimated light from each lens. They're small, so they're still somewhat divergent. But this creates, what's essentially a flat phase across this whole region. And so you get mostly a single spot, mostly. So in practice, this is what it looks like. You have with no lens array. This was the picture shown before. This isn't a perfectly phased array, as you can see, but that's not the point. The point is what I'm showing here is all the different orders. If you put a lens array here, you mostly knock down all the higher orders, and you get only the center one. You do get some in the nearest ones. Some light does get to them. And that has to do with how perfectly you can match the numerical aperture of your emitter to the lens. And we did a pretty good job, but it can be done a little bit better. But unless you have a emitter that's a true top hat, it's never going to be perfect. Okay, so we made a bunch of devices here. The first one I'll talk about is an 8x8 array where we have phase adjusters at every element. So this is the picture I showed before. It's just modestly sized array, but we can do full steering with this. So we can use that first to correct any phase errors, and that's what's shown between A and B. We go from a pretty good spot to something which is a near perfect sync function. And then we can scan it around. And we did do a movie. I don't have a movie to show you, but what we did do is a long exposure where we can move the beam around and we can draw an A. As I said, the other goal here is to have something that's broadband. This device ended up being peaked around 1460, which is not where our laser was centered. But you can see it does have a very broad spectral sensitivity. We can also use this as an imager because, as I said, that's the goal. So we, it's the same chip, and we had this target. It looked like the A and the Draper symbol, the caret, and we could scan the A and see it with this chip. So this is fairly unique, right? This is natural light, and we're actually imaging without other than the lens array, which is very small. There's no other lens here. So it's imaging without a lens. So we do a larger array because we want to be able, to scale it, right? We want to be able to do better resolution or larger fields of view, et cetera. But we didn't have enough heater elements because, I showed before the example where they had 8,000 DACs, but we didn't have that capability. We only have 64 to control. So what we did is we put a heater element at every 8x8 group. So this was not sufficient to fully steer, but it was sufficient to phase up any of the errors in the system. So we go from, with the heaters off, the spot's not very good. We turn the heaters on and we phase things pretty well. And we get a pretty good quality beam. And then we could use this to do imaging similar before. Unlike before, because we can't steer fully, we're using a steering mirror. So we're just using this as a single point sensor essentially, and steering with a mirror. But we do get reasonable imaging out of that, and we can see imaging a target at the back of the room. This is a picture of a camera, and this is a picture of the raw data, and we can correct for some of the fact we don't have a perfect, there is some background in our system to correct for that, and we can see we are resolving features there, 5 millimeters or about an arc minute. Just for fun, because there's nothing I prefer doing than standing on a rooftop in March at night. We took an image of the moon, and target's a little further than 18 meters, and obviously it's natural light. We can't cheat here, and we can see that we did in fact get an image of the moon with this. Okay, now onto the second part of my talk, which is the lens-assisted beam steering. So this works a bit differently than an optical phased array. How this works is very similar to a camera. It's basically a camera in reverse. You have a chip, and we're going to control where the light comes out of the chip. And then you have a lens that basically just focuses that light into a given direction. So a camera would do it in reverse. Camera lens takes the light coming in, focuses it down to a spot on your film if you're old school, CCD if you're not. And we're just reversing that process. We're controlling where the light comes out of a chip, and then the lens then focuses it in a given direction. Probably the most simple example of this is something that is being done today commercially. You put an array of VCSELs here, and you just turn, which are small lasers, and you just activate the laser you want that points the beam in the right direction. Very simple example of this in principle. It's called electronic steering by some people. Other people call it image-based steering. And this works, but VCSELs are somewhat limited in brightness, so this limits your LiDAR range. There's also a lot of applications which you just can't use a VCSEL. Coherent LiDAR obviously is one of them, because you don't have the coherence in a VCSEL. And if you're doing optical comm, you're pretty limited if you use a VCSEL. So I think this is interesting, but it's not going to be the focus of this talk. I'm going to talk about non-VCSEL based lens-assisted beam steering. And so these systems are going to use a chip and an off-chip source typically. So you have an off-chip source that pumps light to the chip, and then on the chip, there's a series of waveguides and switches that direct the light to desired emission location. And then, same thing happens. You emit, the lens takes it and points in a given direction. And so how these different systems work is, what makes them different is there could be different types of switch arrangements. There's trees, switch trees, and there's a row column matrix, and I'll talk about those. You can also use a 1D or a 2D method of steering. And the 1D method works very similar to what we described before with the optical phased array, where you use wavelength steering for steering in the second direction. Generally, these do match in a certain way that generally the switch tree goes with the 1D arrays just because the switch trees are large. But it doesn't necessarily have to be that way. So I'll talk about the switch tree first. Once again, the gray box is what's on a chip usually, and we have an off-chip source. The red light, or the red line rather, is the path of the light. So it comes into a switch, and then this switch, say, directs it up, this switch directs it down, this switch directs it down, and the light goes to only a single grating shown in red. None of the other, unlike the optical phased array case, in this case, none of the other gratings see light at a time, just one at a time. And this is typically done with a long grating so that you can do 1D. You do a 1D array, and then the long grating will steer in the other direction, just like an optical phased array. There's some exceptions. Some people have done 2D arrays with this method, but the 1D array is much more common. So here's an example that was presented by a group at Clio a couple years ago. And they have an off-chip light source. They have this Mach center switch interferometer switch matrix that directs the light to any one of these emitter arrays. These emitter arrays are basically another name for grating. They just call them emitter arrays. And so what happens is, the switch then sends the light to one of these gratings, and then a cylindrical lens will then focus the light in that direction, across the grating path here. However, in the grating, in the direction of the grating, you get the emission that depends on the wavelength of light. And so again, you get the steering in two directions. The labs switching gives you steering in this direction once again, but now it's being done by switching to a particular gratings, getting a light to that grating, and a lens which focuses light in a given direction, or collimates light in a given direction. But in the other direction, the lens has no power. It's really the grating doing the work. The grating is essentially focusing the light and steering it in that direction. So here's another example. This is done by a group at MIT and nearby at MIT Lincoln Lab. And they've actually done it looks like, I don't have much inside information on it, but I've seen some things in the press that they've done a startup called Kuiper Photonics. So in this case, it's notionally very similar to what I just showed. They just reverse the order of the lens and grating. So now you actually have a lens that's before the grating, but optically it's the same. You just have a grating and lens and grating. You can put them in either order. But because they do it this way, this allows them to put the lens on chip. So you don't need an external lens anymore, which is great from a building a system point of view. You don't need to have an external optic. It's cheaper, right? It makes everything a lot easier, and no assembly required either between the lens and the chip. So so that's good. The disadvantage here is that because the lens is on chip, you can see it's kind of a small lens relative to the size of this chip, and that's somewhat fundamental. It's going to be hard to make a big lens here, and so you're limited in how, just like in the MEMS mirror case, you can be limited in how big of a lens you're going to be able to do here. But otherwise, I think it's a really clever idea. Okay, so the other method of switching is switching the light is a 2D matrix of switches. So instead of a tree, you have as shown here, a row column sort of arrangement where light comes in again with the path is in red. Some of these switches are off. If the switch is off, the light just goes straight through. So we go on this bus at the top where the light's going across. When this switch, we hit the switch which is on, and it then diverts the light to another bus going down where it passes through, in this case, if switches are off. And when it reaches a switch that's on, that switch then passes that light to a grating, which then emits light towards the lens. And the two types of switches I've seen in literature are ring resonators and Mem switches. So I'll start with the ring resonator case. Actually, in this case, they use both. They use a Mach-Zehnder tree and ring resonator switches. But again, my apologies. I'm not going to talk too much about how ring resonator switches and Mach-Zehnder trees and Mach-Zehnder switches work. But Mach-Zehnder switches, I will say, tend to be large. And ring resonators are small. And the other property about ring resonators is that they're kind of finicky. They need they work on a single wavelength, and that wavelength is very fabrication dependent. So typically you have to have lookup tables and know the right wavelength, and that each one's going to operate at or tune it. And then you also have to, if the temperature changes, they can change too. So ring resonators work great in that they're small, and they actually have the property that they're low loss in the light that passes by in the off position. I should have mentioned that in the previous slide. That another thing you want here is you want switches that are low loss so that the light can go by, right? You don't want the light, if the switch is off, you want no loss so that the light doesn't die out, basically, right? Because you're going to want a lot of switches here. So you need something that's extremely low loss in the off position. You also need a switch that's small. And ring resonators do fulfill that, but they're hard to control. They did another thing here, which is pretty interesting, in that they had the ring resonators are actually two devices in one. They built gratings into the ring resonators themselves, which is pretty clever. And so now you have a device that not only selects the light, but it emits it at the same time. And this will be a theme we'll return to later. But you get two components in one, which is really convenient because you are trying to minimize the size here as much as possible. The last thing they did is they used a meta lens, which is just a flat type of lens, where they create an index slope in the material using metamaterials. But this technique with the ring resonators and switches would work just as well with any lens. They just happen to use a meta one. Okay, I will now switch to talking about the Mem switches. Now there's two types I will talk about. The first one is done by this group at Berkeley. So this is done by the group at Berkeley. They presented on the Lidar application in 2020, but they've actually, these switches have been, I think they first presented them in 2015, 2016. And how these switches work is they work a lot like a overpass for a highway. And I don't know, I call them overpass switches. That's what we call them at Draper. I haven't talked to Professor Wu to see if he uses the same name. Anyway, but I think it does help in understanding. And so in the off position, what you have are these waveguide structures. Is basically a two-tiered structure. You have a lower waveguide and an upper waveguide. And the upper waveguide is suspended above the lower waveguide and has this bent path in it. The lower waveguide just goes straight across. And in the off position, it's suspended as shown in this diagram. And so at this point, this waveguide's far enough away from the lower one that there's no interaction at all. And the light just goes through. And this is shown in this inset over here, where the light comes in at the top and just goes straight through. And that's because this is suspended far enough away that the optical fields don't interact. When the switch is activated, though, this gets lowered, and shown schematically in this figure here in the on state. And so when this gets lowered, the light can couple from the lower, or will couple from the lower waveguide, to the upper waveguide. And then there's another section of this waveguide which basically slopes up, goes around the bend, and then the whole process reverses. It gets the waveguide slow. Oh, sorry, I'm going the wrong direction. The light slopes up, comes in, it slopes up, goes around the bend, slopes down, and then there's another structure, and these are tapers that will push the light back down into the lower waveguide. So they first developed these switches, I think, for telecom, sort of applications or datacom applications to make a switch, to make it sort of add drop network. But they realized that they could use this for LiDAR too. So just basically having, as we, that sort of row column, a row column matrix, just as we showed, right? The light comes in here, you have row selection, the first set of switches, and then along each row of waveguide, you have column selection, another set of switches. And then the switch doesn't emit the light though. It then connects to a grating, which then emits light towards the lens. So this method has a lot of advantages. It's fast, it's low optical loss. It's practically no optical loss in the off direction, which is perfect. The control is very simple, right? It's just on or off. There's no, unlike the ring resonators, it's not that hard to control. It's not wavelength sensitive, particularly. They've demonstrated them to be quite reliable. Disadvantages are, one, it's a MEMS process, which it's not something everybody does. It's not a particularly hard process, but it is not standard CMOS. And the other disadvantage is the these are somewhat large. So these, this whole thing from corner to corner is about 100 microns. Is the cell size from these switches, and then you also have to add the grating to that in addition. So you can get these fairly compact, but not as compact as you'd ideally want. So to solve the need for a more compact switch, we came up with a variation on this, which combines the gratings and Mem switch into one device. So this can be up to 4 times more compact than the prior Mem switch. We believe 25 by 25 microns should be possible. So this makes it scalable to very large arrays, perhaps up to 1,000 on a side. It also turns out, well, I'll get to this in a minute, but it also turns out that the grating, its geometry is very efficient at producing grating. So the switch works, again, it's somewhat similar to one before. We start with a MEM structure in the on position. It's held above the waveguide. So we have this MEMS grating, it's held above the waveguide in the off position, and the light can just go straight through and there's no interaction. When we turn the switch on, the grating comes down. It doesn't actually touch the waveguide. There's little dimples that control the gap very precisely. And but at that point, the light does interact with the grating evanescently, and it will emit light towards the lens. And it turns out this geometry with a grating above a waveguide with a gap actually can produce very efficient gratings. So it's really ideal. So we've done some tests. I'll walk you through our development path here. We started by developing these gratings, just making sure we can get good optical emission, because that's really the key to making this work, is can we make these gratings and how well do they work? The gratings we design are aperiodic. So we do adjoint optimization to design these gratings. Again, the grating does not actually touch the waveguide. There's a space here. Now, this is a MEM structure, so we don't have the ability to suspend the grating in midair. We just use an oxide, but turns out it doesn't actually change a whole lot when you do the modeling, having an oxide here versus air. And then you can always adjust the design a little bit to make up for it. And I should point out that these devices were designed for 1550, but with these materials, we can work at 905 nanometers too, because the waveguide is transparent at 905. And even though polysilicon absorbs a little bit at 905, it doesn't absorb much. So you maybe absorb 1% of the light with the polysilicon at 905. So here's the results of those. We compared, here we have compared our predicted and our measured values, both in terms of, how efficient the device is, and we show that we get very good efficiency, 75% in theory. We measure about 73%, although there's probably about 5 to 10% error bar on there. So within, or we're matching very well. In addition, not only are we matching well in efficiency, but when we predict, what does light come out of it? Is it coming out straight up, and what sort of direction? We get very good agreement, including we even see these side lobes that we would be predicting. So we definitely feel, this isn't terribly surprising. I mean, the FDTD modeling is pretty robust, and you'd expect to get good agreement between theory and experiment. But it means we're making what we want to make quite well. We also did mechanical test structures. So these tests, I just showed tested the optics of the grating. Now we're going to test the mechanics of the grating switch, but there's no optics to this yet. It's just a mechanical test structure. So we did this because we wanted to test this stuff quickly. We didn't want to go through developing that full process before we understood how this was going to work. But we, don't worry, we'll get to the full process in a minute. So we simplify the structure to focus on the MEMS mechanical properties, so no waveguide. It's just no bottom electrode, but we do have the nitride dimples to define the gap. And so these mechanical test structures really demonstrated really great performance. We got more than 9 billion cycles. We didn't observe any change within our ability to measure with the experiment. The actuation voltage for a MEMS device is fine. 30 volts is what was expected. We got switch speeds of less than 4 microseconds. We just can't measure faster than that. So we think it's probably closer to a microsecond based on resonant frequencies and modeling, but that's as fast as we can measure. Okay. So next thing we did was we looked at we wanted to make the whole chip, right? We wanted to combine the waveguides with the grating and the switches and put it all together. So we started with the structure we built was a serpentine path. So we could do a 2D scanner, even though we only had one type of switch. And we did a 10 by 10 array. In this case, we direct light by activating one switch. Now, long term, we do intend to add another switch so that we can do that row column selection. But our initial work was just focusing on this in this grating switch. Here's a picture of a device that we fabricated. So this is the full device. You can see the grating. You can see these are the spring structures. You can see the waveguide underneath. These things on the side are electrical paths. And yeah, so the other thing to point out is the materials we use is polysilicon, silicon nitride, oxide, and of course the silicon wafer itself. So nothing exotic here, all standard CMOS materials. Here's an image of the 10 by 10 array. This image was taken before the stiffener structure. Let me just go back. Yeah, I forgot to mention. So there's also this structure on top. What that does is it makes the whole thing stiff between the springs so that you don't get any flexion between where the dimples are, because that sets the height, and where the grating is. So that keeps everything stiff and parallel. Okay, here's an optical image again, and of the 10 by 10 array. You can see the serpentine path in the CAD. You can see array of devices. Note that the gratings flip direction depending on which way the light is. And here's a movie where we switch the light slowly so you can see in detail how the light is being switched. And you can see we get very good contrast when the switch is on between the light coming out of the grating and the rest of the field. There is, when the switch is off, some light does hit some defects. We suspect that won't be the case. And the camera can keep up, basically. And it's not working again. Okay, well, I hope you saw that. It seems to be crashing my computer. Okay. And last we did some Lidar data with this chip. Now this chip, it's challenging to do Lidar work with it because we didn't have fiber couplers on it, so we lose a lot of light getting light onto a chip. We also, the way we did detection here is we just had a staring detector that just saw all the reflected light everywhere. We didn't have any spatial selectivity on the detector. And it's also a very small aperture. So this is less than ideal, and yet we still got it to work. And I think that speaks to how the good quality of a beam we get out of our system. and we were able to see a target, in this case, 12.5 meters away, which is really limited because of that high loss we get getting light onto the chip and also the small aperture of the detector we had. Okay, so hopefully I'm on time. Let me just summarize our work. Or summarize my talk rather. I talked about OPAs which are optical phased arrays and lens-assisted beam steering systems. They provide two different ways of steering a beam using a chip. An optical phased array, you have many emitters working together to create a beam. On a lens-assisted beam steering, you're just steering light to a single emitter, and then the lens does the work of creating the beam. Comparing the two, a lab system is easier to control. You're only switching some switches. You're not trying to adjust the phase on thousands of elements. But optical phased arrays eliminate the needs for a lens. So, so that's a trade-off there. Optical phased arrays always need wavelength steering because you can really only make a one-dimensional array, at least for LiDAR applications. While some lab systems, you can do it either way for a lab system. It's viable with or without lens wavelength steering. And then we also talked about some of the specific, I talked about some of the specific Draper work. We did a lensless imager with an optical phased array or an optical phased array-like device. And we use this H-tree arrangement, which allowed the optical phased array to work over a wide wavelength region. We're not suggesting we do this for LiDAR because of the narrow steering range, but it's an interesting way to do imaging because you don't need a lens. We also talked about the unique Draper MEMS grading switch. So this was used in a lab steering device with tight pitches. So I think this is really where it's exciting because you just need this switch can be put very close together to make a very dense array and steer the light very accurately. And again, as promised, here's my email again, Spector, first initial, last name @draper.com. And also as promised, here are all the references. So if you want to grab a screenshot or if there's one in particular you want to see, here they are. Thank you. I hope you enjoyed my talk.
Thank you, Steve. That was great. It does look like we have a couple of questions trickling in here. So let's see. We have Amit Agrawal is asking, could you comment on the polarization requirements or lack thereof?
Oh, yeah, it's, so I assume we're talking about our Mem switch, and it is very much a polarization single pole. I'll make no bones about it. It's a single polarization device. The waveguides are typically single polarization. You might be able to force the other polarization down the waveguides, but then you need a different kind of grading. And it's very hard to, you really couldn't. We have looked into ways of doing polarization tricks. I can't say that much about that. But as I showed, it's very much a single polarization device.
Okay. Jim Fina, hi, Dr. Fina, is asking on slide 26, can you say what approach was used for phasing the array?
Yeah, I'll go back, although I think I could probably do it without it. Yeah, so this was done with, so heaters provide the phase shift, but you're probably asking about the algorithm. It was a hill climbing algorithm, so where you basically go up and down and just go with each heater, right? Is this result better? Nope. Okay, I'll go the other direction. Is that one better? Nope. And just basically go through them all that way. So is pretty simple. We did modify a little bit, I think, to speed it up, just in terms of how far we jumped at different times in the algorithm. But that was basically the approach.
Okay. Just a reminder to anyone else who might have questions, you can go ahead and enter them into the chat. Steve, it sounds like the technologies you've developed at Draper are still kind of early on in the development. Do you see an application in mind for like the lensless imaging and your specific MEMS switch device?
Yeah, I can't say anything about the lensless imaging. We do have an application in mind. We are going forward with it, but unfortunately, I can't say anything about that one. What I can say is this one, we're very much, this switch is very targeted right towards LiDAR. We're looking at, we're actually, and the other interest is in free space optical communications because it's broadband. That is particularly interesting for that, unlike optical phased arrays, which are not broadband. So those are the two applications spaces that we're primarily interested in for this technology. You know, I can't say where we are. We are, you know, we have discussions with, you know, Draper doesn't manufacture. Draper, we are a nonprofit. You know, we'll do small things for the government, but we're not going to, you know, we're not a company that's going to be interested in developing the full system here. We're really, you know, we're like Lincoln Lab and MIT, these sort of places where we're trying to get this to the point where somebody will take it and run with it and license it. And, you know, we've had discussions, you know, some of this work in the past has been supported by, I can't say who, but was supported by companies that were interested in technology. We're still doing work with current sponsors trying to advance it. You know, it is at the proof of concept phase. I do think though, you know, right now we're limited by our foundry capability at Draper. We are a MEMS fab, we're not a CMOS foundry. So we can't pump out large arrays of devices. But I think once we transfer this to a foundry where we can make large devices, I don't think there's a lot of maturing left, actually. It's pretty simple compared to an optical phased array. You know, we have to establish yields and you know, and the process and things like that. But there isn't a lot to get from here to there in terms of the chip itself. You know, building a LiDAR is, you know, another part of, you know, of the process, but people know how to build LiDARs. The switch itself, it works. It's pretty simple. There's really not a lot to do left except to scale it, which I think is pretty straightforward.
So it's less about the technology and more about the processes.
Yeah.
Just we had a couple more questions. How do you mechanically actuate the MEMS switches?
So it's electrostatic actuation. So it's actually a good drawing to pause on. Yeah, so you know, basically there's electrical connection to the top and electrical connection to these pads below. So the pads are, you know, there's a pad under here and there's a pad under here, and you basically put opposite charges on the two. You get electrostatic attraction and it pulls it down.
Okay, and Frank was asking how large an angle can be scanned with the Draper MEMS-based array?
So one of the nice things about this I didn't get into is it is dependent on the lens. You know, you can put any lens you want in front of this chip and you can get any angle that your lens can deliver. So unlike an optical phased array or a lot of techniques, right? It's just like a camera. I can put a wide angle lens in front of it, or I can put a telephoto lens. And there are laws of, you know, how lenses work. You know, and you do get less light collection with a wider angle lens. So if you want to see to a large angle, you make that sacrifice. You don't have the long focal length or large aperture size. So it can, you know, there are trade-offs in terms of range and things like that for a given, you know, amount of power and time, et cetera. So you collect less light with a wide angle lens than you will with a narrow lens typically. But otherwise, you know, it's limitless. It's really up to your lens.
Seems to be a common answer in optics. It depends. Couple more questions for the LiDAR assisted, or sorry, the lens assisted LiDAR. Is it possible to use a source array, VCSEL or LED instead of array of grading emitters?
Yeah. In fact, I mentioned, I did mention in the beginning, you know, it's sort of a different technology, so I didn't talk about it because it is so different. But you could just simply put a VCSEL array in your focal plane and turn on and off the VCSELs. Yeah, sorry, I mentioned that in the beginning, but I won't bother going there. So it certainly can be done, and it is done. It's just a different technology, and you know, as I mentioned, the disadvantage to that is, you know, your VCSEL can only have so much brightness. So if an edge emitting laser, you can have a lot more brighter source, so you can put a lot more power at a small spot, which can allow you to get to greater range and things. But the VCSEL is a completely legitimate technique of doing it, and people are doing it.
Okay. For the new MEM switch, can you comment on how robust you expect it to be against mechanical vibrations?
Yeah, it's extremely robust against mechanical vibrations, actually, because the resonant frequencies of these switches are megahertz level. So you're not going to get any acoustic coupling to that. And so, yeah, they're pretty much, nothing's going, unless you're shooting them out of a cannon or something, I can't see anything affecting them.
Okay. And what is the wavelength bandwidth requirement, narrow or wide, for the Draper method?
Well, it's more of what's, what can we accommodate? It obviously can work with narrow. So we are, I think we're going to publish something on that soon. But it's determined by the grading, really. So your grading has a certain bandwidth, depending on what you want to call it, 3 dB or 1 dB. But gradings, you can estimate the bandwidth from that, but it's 10, 30, depending on what tolerance, 50, depending on what tolerance you can have for loss, sort of bandwidth.
Gotcha.
Actually, maybe more than that, actually, now I think about it. I think with a few 1 dB, it's probably more on the 30 range. And then I think you can get to almost to 100 dB with the, if you're willing to go like 3 dB loss. But sorry, I don't have the exact number off the top of my head, but it's relatively broad, right? It's not like you can cover decades of bandwidth, but you can, compared to other methods, it's fairly broad.
Sure. Okay. I haven't seen any other questions pop up, and I think that's this is a good time to wrap up. Steve, I think we've taken up plenty of your time for this evening. We really appreciate you being here and presenting your talk on interesting stuff that's going on at Draper. Sounds like we might have to have you back in a few years.
Yeah, hopefully, hopefully we'll have the real system all matured by then. That's dope.
Yeah, we'll have David Lees pester you every so often to see how you're doing.
Okay, well, I see him periodically, so you can do that. Yeah.
All right. Well, thank you everyone for coming. Thanks again, Steve, for joining us. Hopefully I will see all of you in February, and everyone stay safe.
Thank you.
Thank you.
Bye.